Thank you. Thanks for giving me this chance of talking to you guys about our experience using Kokkos inside E3SM. E3SM, which stands for Energy Exascale Earth System Model. It's the DOE's State of the Science Earth System Model. It's got several components, just like other planet models: atmosphere, land, ocean, land ice, sea ice, just to name a few. There's a few more. And all these components can run different resolutions on a variety of grids and different time and space scales. Most of E3SM is written in Fortran 90 to be precise, but there's also a few other languages being used, not to mention the build system, which has tons of different layers, different languages, but the code itself is mostly Fortran. So in the last decade, there's been a push for E3SM to reach exascale. And this push was driven by a few factors. One is that decision makers need more reliable climate prediction, most importantly with reduced and quantifiable uncertainty. One of the tasks was to develop a much higher resolution for the atmosphere component to get rid of some parameterization and hopefully reduce uncertainty. And that led to resolutions and grids that were like very, very large. And the other factor pushing this exascale push was that we finally had like machines that were at the edge of exascale. Most of these machines were using accelerators and GPUs. So this led to a series of efforts in E3SM, not just one, to utilize these machines, almost exascale machines, and now we're breaking exascale, to answer important science questions. In particular, our task was to make sure that E3SM could run efficiently on all the large DOE supercomputers, most importantly on the GPU-based ones like Summit, Perlmutter, and Frontier. First two use NVIDIA GPUs, the last one uses AMD GPUs. So a key word or expression here is performance portability, and by that we mean being able to, for a code base, to run efficiently on a variety of computer architectures, where efficiently can mean different things, but generally speaking, one can think of achieving a good performance, where performance means a certain threshold of the maximum achievable flops or memory bandwidth on the given machine. Now, different applications will reach different thresholds, because if you're embarrassingly parallel and you just have dense kernels, of course you'll utilize well flops. But if you, for instance, got a lot of communication, then this maximum achievable bandwidth for you will be different. Anyways, so there are mainly three approaches to achieve performance portability. And the first one is compiler directives. So you use preprocessor directives to hint or force the compiler to optimize, reorganize the code to target particular threading models. And OpenMP and OpenNCC are the most common examples of this approach. The second approach is to use general purpose libraries. So you delegate all the stuff that has to do with architecture specific and also threading model specific choices to a third-party library. Kokkos, Raja, HPX, Okka, they're all examples of this kind of libraries. And then, as we heard already a few times in this workshop, there are domain-specific languages and libraries. So you add an intermediate compilation step to generate an optimal source code for the given architecture and threading model. Cyclone grid tools are an example of this. So you start from a language that is not the native language, you run this interpreter and you generate an optimal source code, which then is compiled with the standard compilation tools. So all these approaches have some pros and cons. So I'm not going to say which one is best, because none of these is best than the other one on all levels. But these are the approaches that you can see commonly in science. So to achieve performance portability, there's three key ingredients, and some are more important than others on particular architectures, but they're all in general important if you want your code to be performant on a variety of architectures, not just on a particular one. So these three ingredients are, you got to expose as much parallelism as possible. So all the layers in your algorithm and code that can be parallelized, you got to be able to expose them so that the threading model in the backend can exploit this. The second is maximize vectorization. Vectorization is one of the cheapest and most effective ways to achieve to get flops per watt of power on CPU architecture. So this is mostly a CPU centric important aspect, but not necessarily just CPUs, a little bit also in GPUs to some extent. And then the third important aspect is minimize memory movement. This can mean when you're dealing with accelerators and GPUs, this is of course hinting at limiting the transfer between device and host memory, but there's also the cache aspect on CPU-only machines. For instance, you got to be able to read from memory as little as possible, do as much work as you can with a given chunk of memory data, and then rewrite to memory. That's also something to keep in mind. Moving memory is generally more expensive than doing calculations. Okay, so these are the concepts I wanted to bring up regarding performance portability. Now, one of the paths we chose to achieve exascale and performance portability in E3SM is using Kokkos. So what is Kokkos? Kokkos is a C++ library that handles on-node parallelism. It's developed mainly at Sandia National Labs, but there's a few contributors elsewhere. Kokkos mainly provides some abstractions and constructs for expressing concepts related to parallelism. These include execution space, for instance, OpenMP versus CUDA, HIP, SYCL, or whatever. Execution policy, so how you map your amount of work to the threading model. The main two execution policies are a range policy, so you just loop through the items in your, let's say, a for loop, or a team policy where you group threads into teams that can share some memory, then they can share some common work and recycle some stuff. And then the concept of a parallel operation. Are you doing a for, a reduction, or a scan operation, for instance? It also provides constructs and abstractions for multidimensional arrays, including what's the data type. This barely means int, double, float, whatever it is. Then the memory space, which is where is this array stored, on host, on device, what kind of device memory. The layout, of course, you need to know what kind of multidimensional array it is, and then how you're going to access and handle memory. Is it going to be a random access? Is it going to be Aliasing error vectors? Are you going to are you in charge of deallocating the memory? Is that automatically done? And all of that stuff. Kokkos supports, as of now, several backends, including the most common one like OpenMP and CUDA, but also HIP and SYCL and others. So when we integrated, when we used Kokkos inside E3SM, we started from the atmosphere component. In E3SM, it's called EAM, E3SM Atmosphere Model. I don't know if that stands for E3SM Atmosphere Model or Earth Atmosphere Model. I think it's E3SM Atmosphere Model, probably I should know that. So our guiding principle in regard with the three key component of performance portability, were the following. So in order to expose parallelism, we took advantage of team threads, which basically is a way to say we used hierarchical parallelism. These can allow to share common work and minimize index bookkeeping. To maximize vectorization, we had to develop some packed data structure and some masks to perform mask packed operation, and that proved crucial to enhance vectorization in C++. And then to minimize memory movement, the obvious thing that you think is keep data on device as much as you can. When you're working on GPU, that means stay on GPU until you have to do some IO operation, or until you have to couple with other component of the Earth model that are host only, which in E3SM is any other component as of now, although development is happening for GPU friendly components. But that's one scenario where you have to copy data to host. But that's not just it. As I said, minimize memory movement has to do with also like reutilizing cache and being careful on how you access memory. One of the things that we had to do is for instance, use some minimally sized scratch pads, some scratch memory within parallel loops to minimize memory consumption and also increase locality of memory access. So this effort started about 4 years ago with porting the hydrostatic dynamical core in 2020, we did a similar task with a non-hydrostatic dynamical core. And then in this year, we're completing the boarding of the full atmosphere component, which includes, the physics parameterizations. Right now, we're handling ultra high resolution, as I mentioned earlier. So that means like 3-kilometer resolution and cloud permitting, cloud resolving models. So that does away with deep convection parameterization, but we're going to support that going forward too. So that was the timeline of our effort. So what about performance? So for the die-core only, here I'm showing some results that we submitted supercomputing in 2020. We simulated the NGPPS benchmark, which includes 10 tracers, and we ran it at 3 and also 1 kilometer horizontal resolution. On the top right, I'm depicting the typical working element of the die-core. So you have a 2D element on the sphere, and E3SM die-core uses the cubed sphere. And then inside each 2D element, you have a bunch of degrees of freedom. We use a spectral element method. So those are the GLI points. And then you extrude this 2D element vertically for a certain number of levels. And that's what we call a one element of computation. And one of these is always belongs to a single MPI rank. We don't divide this element across ranks. So in 2020, we did the submission to supercomputing, and we were running the die-core at 3 and 1 kilometer resolution. Some improvement happened later, which adding, for instance, semi-Lagrangian transport. And on the right, on bottom right, you can see the performance plot. We scale all the way to the full Summit supercomputer, which has 4,600 nodes. Each node is 6 GPUs, so that's 27,600 GPUs. And you can see the scaling is not perfect, but it's very good. The black line is what we had when we submitted the paper to supercomputing. We were using Eulerian transport. Then, as you can see, the semi-Lagrangian transport added a little more simulated years per day. But we can compare that with the blue line, which was running on host, because the blue line still used the Eulerian transports. But if you limit to the Eulerian transport, you can see that using the GPU added roughly a 10 to 12x speed up compared to using the host. This, as in terms of workload, so if you look at the rightmost point, the 4,600 nodes, we roughly have 225 horizontal elements on each GPU. So that's the workload that we have. And each element is then, of course, extruded vertically, as I depicted in the picture above. But this number will be important in the next slide when comparing to the full atmosphere. So we're currently in the process of running we ported the full atmosphere in E3SM to run on GPUs, including physics parameterization. And we're currently in the process of running the 3-kilometer resolution simulation campaign on Summit. So I don't have the numbers for the full 3-kilometer simulation campaign, but I have some numbers for the 1 degree horizontal resolution. That's roughly 110 kilometers at the equator, still including 10 tracers. So that's the same as before. There's a bunch of lines on the right, but the ones that you probably can just focus on are the yellow line, and then the blue line that is superimposed to the yellow line up to 64 Summit nodes, and then the green line. So the yellow one is the original Fortran implementation. The blue one superimposed to the yellow one is the new C++ Kokkos one running on host, and they perform roughly the same. There's some tiny improvements somewhere, but those are not due to using Kokkos. They're just some slight reworks of arrays, indexing, and better vectorization, for instance. And then the green line is the C++ Kokkos implementation running on GPU. So the host one scales perfectly, and you're probably puzzled, why does the GPU one not scale so well? But as I mentioned earlier, at the rightmost point of the previous slide, we were at 225 elements on GPU. While if you look at the leftmost point here on 4 nodes, we have the same workload on the GPU. So in this case, 4 nodes is given that the problem is smaller, is given the same workload on each GPU, so roughly 225 elements per GPUs. So when we increase the node count, up to 64 elements, 64 nodes. At 64 nodes, we have 14 elements per GPU, and that's very little amount of work for a GPU. We know that accelerators and GPUs, they work very well if you throw a lot of work at them. But in this case, we're throwing less and less work at them. So this is in a way a much stronger scaling of the model with respect to work size. But at the leftmost point in this graph, we can still see roughly 20x speed up of a GPU versus CPU. And even when you go to the strong scaling limit of like 14 elements per GPU, we still get a roughly 2x speed up of using when we get using the accelerators versus the CPU. And again, each summit node has 6 GPUs, so you can do the math of how many GPUs each of these data points is using. And unfortunately, I'm not able to show you the 3-kilometer resolution as I'm speaking. Someone else is running the jobs on Summit. Okay, so I'm gonna just stop here and just discuss some ups and downs of what we did. We're relatively happy with Kokkos, can efficiently map to current and upcoming architectures. We have already some preliminary results. Well, not so preliminary, we're kind of getting kind of stable of using AMD GPUs, and we get reasonable performance on those as well. In a way, Kokkos can be seen as a way to shield us from disruption from new architectures. In a way, we delegate to Kokkos dealing with all the shenanigans of new kind of chips. The speed up we get on GPU compared to CPUs is good, and we also get a good CPU performance. We're on par with the original implementation, so we're not giving up any performance on CPU. Even though the largest supercomputers will likely be GPUs going forward, we still want to get good performance on CPU because we might run smaller problems, maybe ensembles on conventional CPU machines. So that's why it's still important to get CPU performance. Hierarchical parallelism is crucial, at least in E3SM and in the atmosphere component of E3SM, to achieve performance portability, because it allows to expose several layers of parallelism. Sometimes you have, embarrassingly parallel nested for loops. That way you can just flatten and collapse the for loops, but in other cases you need to recycle some work. In that case, hierarchical parallelism is really crucial. For the downsides, well, the elephant in the room is the C++ syntax is way heavier than normal Fortran. It can be a barrier for field scientists that are perhaps more accustomed to use Fortran. There's no way around the heaviness of template metaprogramming. All you can do is try to encapsulate as much as you can into like a library or some limited files, and then expose less complicated syntax to the scientist. The other downside is that general purpose performance library, simple algorithmic steps can sometimes require several lines of code to be expressed in a performance portable way. You can maybe expose them still in a way that is okay for one architecture, but if you want it to be portable, it can still require a few lines of code. And that again can be a barrier for some folks that are not used to C++ code. And then one of the biggest downside on CPU was vectorization. C++ does not vectorize as well as Fortran. And I'm not talking about writing your small main with just adding 2 vectors that will likely still vectorize well, but there are several other factors that impact the ability of a compiler to vectorize in complex codes. And C++, in our experience, doesn't do so well. So we had to write some pack-like, some vector-like structures needed for performance. And that means not only you have to do this, but other areas of the code that before just operated on single reals, doubles, floats, and now need to be aware that there are packs. So if you pad the arrays to allow integer number of packs, as a result, you could have some areas of code that now need to keep into account that they cannot just pass this flattened 1D pointer to some libraries, because there may be some junk at some areas of the code. So this requires a little bit more care. So that's also a downside. And I think I'm going to stop here. Thank you.